Hi, I am Chris Palaka, and together with my group mates, we're going to discuss the carboxylic acids and their derivatives. To begin with, what is the connection between the smell of the feet and vomit? You guessed it, carboxylic acids. The smell of the feet is partly due to the presence of isovaleric acid, which is produced by the bacteria living in your foot skin. These bacteria also turn odorless underarm secretions, such as amino acids, into malodorous molecules, which include carboxylic acids. The stench of the vomit is caused by butyric acid, produced by the bacteria in our gut. Given these awful smells, you might wonder, why do you want to work with carboxylic acids at all? The taste of vinegar, the sting of an ant, the nasty smell of the feet, and the relief derived from aspirin, all of these are due to the compounds that belong to the most important family of organic acids, the carboxylic acids. The resilience of polyester and nylon fabrics, the remarkable properties of Velcro, the softness of silk, the no-calorie sugar substitutes, the strength of bacterial cell walls, and the strength of our cell membranes, all of these are due to properties of derivatives of carboxylic acids. The functional group common to all carboxylic acids is the carboxylic group. The name is a contraction of the parts, the carbonyl and hydroxyl group. Carboxylic acid derivatives are compounds in which the hydroxyl part of the carboxyl group is replaced by various other groups. All acid derivatives can be hydrolyzed to the corresponding carboxylic acid. The carboxylic group, COOH, is the functional group of carboxylic acids. A hydroxyl group is directly attached to a carbonyl group, and the interaction between them affects the reaction pH. Thus, the polarity of OH bond is greatly increased, and the tendency to release a proton is higher than alcohols or even phenols. Direct addition of nucleophiles to the carbonyl group is also less likely. However, the carbonyl oxygen is directly protonated in the presence of strong mineral acid. The resulting organic cations can then be combined to a nucleophile to form a new band of carbon at the carbon atom. Ester and amides occur widely in nature. Anhydrides, however, are uncommon in nature, and acid halides are strictly creatures of the laboratory. As you'd expect, carboxylic acids are acidic. If they have 4 carbons or fewer, they can dissolve in water. The hydrogen in the COH part of that structure will be partially ionized, forming a hydrogen ion leaving behind carboxylic ion. In addition, carboxylic acids are weak acids because they don't release hydrogen ions into solutions as much as strong acids like hydrochloric acid does. The COH part of these structures allow intermolecular hydrogen bonds to form between 2 acid molecules, or an acid water. Furthermore, carboxylic acids have high boiling points, and all of these with fewer than 10 carbons in straight chain are liquid at room temperature. Here, we can react shorter chain of carboxylic acids with sodium or potassium hydroxide to form water-soluble salts too. The hydroxide ion grabs the proton from carboxylic acid group, forming water and leaving a carboxylic ion behind. And now, let's listen to Althea as she discusses the acidity of carboxylic acids.
In acidity of carboxylic acids, there is water solubility reaction to litmus. Place 2 ml of water into each of 3 clean dry test tubes and add a little of the acid be tested, which is the 6 drops of glacial acetic acid or a small pinch of lauric acid or benzoic acid. Shake to mix and examine. If the contents of the test tube is heterogeneous, set it aside for the next test. Otherwise, test the mixture with a small piece of the blue litmus paper. That is the procedure. For the results, acetic acid with water makes a homogeneous mixture, soluble in water, and appears red in a blue litmus paper. On the other hand, benzoic acid with water makes a heterogeneous mixture, insoluble in water, and appears red in a blue litmus paper as well. Below are the chemical equations involved. When acetic acid CH3COOH, which is a weak acid, is mixed with water, some of the H come off of the COOH group of the molecule. Then they are given to nearby water molecules, and so 2 new ions are produced, CH3COO, which is known as the acetate, and H3O, which is a water molecule with an extra H and is known as the hydronium ion. Therefore, there is an equilibrium between all of these substances. Second is the solubility in aqueous base by salt formation. Procedure: to the heterogeneous mixture obtained above, add 10 drops of 40% sodium hydroxide and shake thoroughly until no more changes occur. If the acid has dissolved, test the reversibility of the reaction involved by adding 1 ml concentrated hydrochloric acid. For the result, benzoic acid with sodium hydroxide makes a homogeneous mixture and is soluble in aqueous base. On the other hand, benzoic acid with hydrochloric acid makes a heterogeneous mixture and insoluble in aqueous base. A weak acid like benzoic acid will react with a strong base like the sodium hydroxide in a neutralization reaction. It also happens to be a double displacement. Now, does benzoic acid reacts with hydrochloric acid? The answer is no. Benzoic acid will react with bases, but hydrochloric acid is the opposite of a base. Benzoic acid can sometimes react with things that are very strongly positive or negative, but neither H plus nor Cl minus are powerful enough to make that happen. Therefore, there is no reaction.
Third is the action of sodium bicarbonate. Place 1 ml of 10% sodium bicarbonate solution on a watch glass and add a little of the pure acid, 1 drop if liquid, a little powder if solid. Perform the test on acetic acid, benzoic acid, and lauric acid and record all observations. For the results, for the reaction of acetic acid and sodium bicarbonate, it is observed that there was a brisk effervescence happening. A brisk effervescence is defined as the rapid or vigorous evolution of a gas in a chemical reaction. And it is also observed that the gas was colorless and odorless. The chemical formula of the observable result was CH3COONA plus H2O plus CO2. For the reaction of benzoic acid and sodium bicarbonate, there was also a brisk effervescence and the gas was colorless and odorless. For the chemical formula of the observable result, it was C6H5COONA plus H2O plus CO2. For the chemical equations involved, acetic acid and sodium bicarbonate react to sodium acetate, water, and carbon dioxide. Benzoic acid and sodium bicarbonate react to sodium benzoate, water, and carbon dioxide. During the reaction, a solid and liquid have been chemically reacted to form a gas and liquid. This experiment can also be used to explain foams as liquids or solids containing gas bubbles. Fourth, we have salt hydrolysis. Dissolve a small amount of sodium acetate in 2 ml water in a clean test tube. Test the resulting solution with blue litmus paper. Note that when blue litmus paper is placed in a substance that is acidic, it will turn red. However, if placed in a substance that is basic or neutral, it will remain blue. Blue litmus paper is meant to test only for an acidic pH level. Now, what is indicated about the relative strength of acetic acid? Acetic acid is said to be a weak monoprotic acid. Now for the result. We have here the structure of sodium acetate. For the reaction of sodium acetate plus water plus blue litmus paper, it is observed that the blue litmus paper retained its blue color. Thus, we can say that the substance is basic or neutral. The chemical formula of the observable result is CH3COOH plus OH. The chemical equation involved is sodium acetate plus H2O reacts to acetic acid plus hydroxide ion.
I'm Reverend Lazar and I am going to be talking about the test for acetic anhydride. But before we move on, let us know what is an acetic anhydride first. Acetic anhydride, or also known as ethanoic anhydride, is a chemical compound with the formula CH3CO2O, which is the simplest insoluble anhydride of a carboxylic acid and is widely used as a reagent in organic synthesis. It is a colorless liquid with a very pungent, penetrating vinegar-like odor, and it is used in making plastics, drugs, dyes, perfumes, and explosives, and aspirin. Now on to the experiment. Hydrolysis. Add about 1 ml of acetic anhydride to 5 ml of water. Do the liquid mix. Next, shake the test tube and warm them gently. Lastly, test the liquid with a blue litmus paper. Result: acetic anhydride dissolves to about 2.6% by water. Because acetic anhydride, like most acid anhydrides, hydrolyzes to create carboxylic acids. Aqueous solutions have low stability. Acetic acid is generated in this situation. As seen below, this is the equation involved. CH3CO2O, which is the acetic anhydride, plus H2O, which is water, gives us CH3COOH, which is the acetic acid. Alcoholysis. Place 1 ml of ethyl alcohol in a test tube. Immerse this in ice and drop by drop 1 ml of acetic anhydride. Neutralize the solution with 10% of sodium hydroxide, and lastly note the other. Result: ethanol with acetic anhydride gives us ethyl acetate. The colorless liquid has a sweet, fruity odor that most people find pleasant. Seen below is the equation involved. C2H5OH, which is the ethanol, plus CH3CO2O, which is the acetic anhydride, gives us C4H8O2, which is the ethyl acetate.
Number 2, test for acetamide. For alkaline hydrolysis, mix about a half of gram of acetamide with about 5 ml sodium hydroxide. Shake and form and carefully note the odor of the vapors. If you add sodium hydroxide solution to a non-organic compound and it gives off ammonia on heating but not immediately in the cold, then it is an amide. You can recognize ammonia by the smell and because it turns red litmus paper blue. The possible confusion using this test is with ammonia salt. Ammonium salt also produces ammonia with sodium hydroxide solution, but in this case there is always enough ammonia produced in the cold for the smell to be immediately obvious. For acid hydrolysis, add 2 ml of dilute sulfuric acid to about 1/2 gram of acetamide. Warm and gently observe the odor of the vapors. Taking ethanamide as a typical amide, if ethanamide is heated with a dilute acid such as dilute hydrochloric acid, ethanoic acid is formed together with the ammonium ions. So, if you were using hydrochloric acid, the final solution would contain ammonium chloride and ethanoic acid.
Good day everyone, I am Kitty Sofia Di Patriarca. Before discussing about the tests conducted in this laboratory exercise, let me give a brief background about esters. So what are esters? The term ester was coined by the German chemist Leopold Millen in 1848. Basically, an ester is an organic compound where the hydrogen in the compound's carboxyl group is replaced with a hydrocarbon group. Esters are derived from a carboxylic acids and usually alcohol. While carboxylic acid has the COOH group, the hydrogen is replaced by a hydrocarbon in an ester. Esters are characterized by a carbon bound to 3 other atoms. The chemical formula of an ester takes the form RCO2R', where R is the hydrocarbon parts of the carboxylic acid and R' is the alcohol. Ethyl acetate and methyl salicylate are the compounds used in this laboratory exercise, and these are their structures. Now, let's discuss about the first test, which is to identify the odor of the following compounds. Esters are typically fragrant, and those with low enough molecular weights to be volatile are commonly used as perfumes and are found in essential oils and pheromones. Moreover, these are the results. For ethyl acetate, it is sweet, fruity, and pleasant, resembling a cherry or a grape, while methyl salicylate smells like mint, resembling the wintergreen. Next are solubility and density. We are instructed to test water solubility by adding 1 drop each of ethyl acetate and methyl salicylate in a 2 ml of water in separate test tubes. And these are the results. As you can see, ethyl acetate is insoluble with water. Both ethyl acetate and water are polar molecules, and due to strong hydrogen bonding in water molecules, the molecules of ethyl acetate do not polarize the water molecules easily, so ethyl acetate is insoluble with water.
while methyl salicylate is slightly soluble with water. For the density, ethyl acetate is less dense than water, while methyl salicylate is slightly more dense than water. Lastly, hydrolysis. Esters can be hydrolyzed under acidic or basic conditions. Under basic conditions, the reaction is known as saponification. On the other hand, under acidic conditions, the mechanism of hydrolysis is the reverse of the Fischer esterification. In this laboratory exercise, we're only focusing under the basic conditions. The hydrolysis of esters in the presence of alkalis such as potassium hydroxide or sodium hydroxide, a reaction called saponification, is utilized especially in the preparation of soaps from fats and oils and is also used for the quantitative estimation of esters. We are instructed to place 1 ml of ethyl acetate in a small flask with 5 ml of 10% sodium hydroxide solution. Heat the mixture under reflux by attaching an 18-inch tubing to the flask damp in an upright position. Continue heating under the ester layer disappears. This will take about 20 to 30 minutes. Change the glass tubing with an obtuse angled another glass tubing and acidify the solution left in the distilling flask. Test the dilute hydrochloric acid. Thus are the products of hydrolysis and the following compounds. For ethyl acetate are ethyl alcohol and sodium acetate with their respective chemical formulas indicated in the table, while the products of methyl salicylate are salicylic acid and methanol, together with their respective chemical formulas indicated in the table. When ethyl acetate reacts with the sodium hydroxide, the chemical equation involved is CH3CH2OOCCH3 plus NaOH or the sodium hydroxide, 2CH3CH2OH plus NaOOCH3C. That's all for our report. Thank you for listening and have a great day ahead.